In this segment, we're going to talk about some of the details behind training and implementation of sequence-to-sequence models. So as we discussed, there's an issue where, unlike RNNs, where you can kind of just run the entire thing, if you want to encode a sentence, for example, you basically run one pass through the model and get a vector out. Sequence-to-sequence models have this property where we actually need to evaluate what's going on in the decoder at each time step in order to predict a next word. And this is a little bit different than what we saw in language modeling. Sort of theoretically it's the same, but language models are typically used to evaluate the probability of like a fixed string of text, and here we're actually like generating new language. So the encoder here is like this part again is a relatively straightforward RNN, and you can use basically whatever whatever kind of encoder architecture you want. The decoder we're going to think of as a separate module that takes as input the current decoder state and also this input. And then it outputs two things. It outputs the predicted token and also a new decoder state that we're going to feed to the next time step. So the reason we're not all thinking of this as one module is because we're going to need to evaluate it at each step to actually get this prediction. So at training time, what we need to do is we need to maximize the likelihood of the observed data. So following the kind of template we've been using so far, what we're thinking about is each of these distributions over tokens basically has some correct value given by whatever our ground truth like translation we're training on is. And we can compute the log probability of the model's prediction of that ground truth token. So at the first time step, what is the probability the model assigns to L? And then take the log of that. And then what we're summing over here in this objective is we're just summing over the time steps of this sequence. And then we're also summing over our training examples, X and Y. So what this gives us is it gives us one term in our loss for each word in this target sentence. And the thing that we haven't specified here is what we're going to do with these inputs at the bottom. And so the most common way of training Seq2seq models is through what's called teacher forcing, where this is exactly what we did when we trained language models. We said, all right, assume that everything up until now matches the gold standard and predict the next word correctly. Now remember that for sequence models, fundamentally what we were doing was we were modeling, probability of next word given previous words. So this was like totally correct to do. For Seq2seq models, what we're trying to do at the end of the day is we're trying to predict a good output sequence Y conditioned on the input X. And we don't care as much about okay, if the whole Y up until this point were correct, what's our best prediction for the next Y? So that's what we're doing here, but it's a little bit weird that we assumed we did everything right because at test time we might actually do stuff wrong. And this is the same idea that came up when we talked about dependency parsing in the transition-based or shift-reduced framework. Is like, if you always assume that the model has made correct decisions, then if it makes an incorrect decision at test time, then it can actually kind of go off the rails because it gets itself into weird states that it's never seen before. So there's an approach to deal with this called scheduled sampling, where what you do is you take the model's predictions, which may be incorrect, and you sometimes feed those into the into the next state as the input instead of the ground truth. And so these little circles here represent basically sampling with probability p, either the gold or with probability 1 minus p, the model's prediction here. So the way that people often do this is they start with p equals 1, which is just teacher forcing, and then over time, as your model gets trained reasonably well, you start to decay that. And so you tell the model, okay, start to consume your own predictions but still try to make the correct predictions at the next step. All right, so this is not a like completely satisfying solution to this problem, because what happens is, let's say that there was a completely different translation of this sentence and the system really wanted to produce that. What would happen is we're still sort of attached to the original sequence. We still have to predict le film était bon at these different time steps. And so we can't just like deviate, produce some other good translation and say, hey, that looks pretty good. So in order to really solve this training problem correctly, we need something like reinforcement learning, where we say, all right, I've got the ground truth sequence, le film était bon, and then maybe I have some other kind of prediction which expresses the same thing, and we have some function which kind of evaluates those and gives you some reward. And now we're going to train this thing as an agent that's going to maximize the reward it gets through its generation. So a lot of times you can get Seq2seq models working a little bit better if you incorporate some extra term as a reward function and do some kind of reinforcement learning with them. But starting with teacher forcing and scheduled sampling is certainly enough to get 90% of the way there on most problems. Okay, so in terms of some of the gory details here, so one of the most annoying things to deal with is the sentence lengths. So for both the encoder and the decoder, we now have variable length inputs, right? And so we need some notion of padding where if we want to make these things into actual tensors that are going to play nicely with our frameworks like TensorFlow, we need to pad them out to turn them into regular shaped things. And then we need what we call a mask, where if we say, okay, we've got these, we're only predicting 5 words in this case, but we've got 10 words in our longest sentence. We need to say, all right, we're going to ignore, what happens in, words 6 through 10 here, because it's not real. It's not happening in the model. The encoder here is going to be a standard RNN. That's fine. The decoder is going to be also whatever you want to use. But because we have to execute just one step at a time, you might need to sort of chop the computation graph up in a slightly different way. And then at test time, you need to for loop over this thing until you generate a stop token, or you run out of patience or hit your limit of how many tokens you want to generate. And at training time, you actually know where the gold stopping point is. So you need to be aware of the fact that you're only going up to as many tokens as there are in the gold. So trying to implement this and batch it ends up being a little bit annoying. The decoder kind of ranges across multiple time steps. Like we have to kind of run it for the first time step and then run it for the second time step. So typically what you need to do is you actually need to process multiple examples in a batch in parallel, basically do all the first time step for everything in your batch, then all the second time step for everything in your batch, then all the third time step, etc. So it's a little bit different from the way we often think about batch processing, where it's like, you just do every example in the batch in one shot and then move on to the next batch. All right, and the final detail I'm going to talk about here is beam search. So what we want to really do, again, is find this argmax over y. What is the most likely output sequence? And that likelihood is given by the product over the probabilities of each token conditioned on what came before. Now, what you get if you just independently max, if you just greedily max at each time step, you don't necessarily get the highest probability sequence here. So beam search is a trick that often makes things a little bit better, but again, it's not a kind of make or break. The greedy version works okay. But I'm just going to briefly tell you how beam search works here. So the way it works is we get our distribution over possible tokens. So we have le, la, and le here with associated probabilities. And then these are going to populate entries in our beam. So after this first time step, we now say, okay, there were 3 things that we could have predicted. And they all actually have the same hidden state vector here. And each one has an associated score, and here is just the log probability of that prediction. All right, so then what we do is, in order to we take one of these states and we expand it. We say, okay, for la, we need to feed la in as input to the next time step of the decoder, and we need to take this hidden state from the previous time step, right? And we take those two pieces, we plug it into our decoder, out pops another distribution, which gives film, in this case, 0.4 probability. And that also gives us a new vector here. And so we could stick that into our beam, our next beam with this score. And we can do the same thing for other options as well. And in this case, le can also produce film as a continuation. And now we get two sequences, le film and la film, which have different state vectors, right? Because the state vector represents the input, and so la and le, or rather the output up until this time step, which becomes the input. So la and le cause this to be different. And so even though our immediate prior word is the same, we have two different states that we need to keep track of going forward in our model. And so unlike in, say, the Viterbi algorithm, where it was the case that when you implemented beam search, like you could combine two things that sort of end in the same place, you could like max over them. Here you can't, because these vectors introduce arbitrary dependence between things in this output. So there's no way to say, oh, okay, I can see that le film is strictly dominated by la film, and we get rid of la film. Like, you have no idea that the vector for la film couldn't change something 10 words down the road, and so you need to keep around these alternatives. And this is why exact search in these models is exponential time, because the state vector depends on everything up until this time step. Okay, so the final thing I'll say about implementing these models is that we could think about what abstractions are being enforced by these different modules. So the encoder is really mapping sentences into vectors, right? Like one vector per token. And the decoder takes a hidden state and a prefix of the output and returns a new hidden state and a new output. And another way to think about this is, we'll see an architecture later, the transformer, which doesn't actually use hidden states at all. And so what I want to emphasize is that there's nothing like special about RNNs or LSTMs. Like, these are the models that were kind of used to introduce these ideas and frequently work well. But there's no reason you can't use like a CNN as an encoder, or a transformer encoder decoder. That's another architecture we're going to see later that looks very different, but still fits into this framework. Or you could do things like use a CNN and then plug it into an LSTM. You can kind of mix and match here. So the reason I'm just building this up is largely to introduce the idea of transformers, and also to emphasize that there's nothing special about RNNs from the standpoint of Seq2seq models, even though they often get kind of rolled up together. So you should decouple those concepts in your mind a little bit. Seq2seq model is this general paradigm of autoregressive prediction of each token, and RNNs are just one way to do that. So what we saw here was how to take this framework and make it a little bit more concrete and actually go about implementing it. And we saw some ideas like, we saw how to train, and then ideas like batching and beam search that are going to be kind of implementation details when you're dealing with this. That's the end of this segment.